Dr. Peter West, who's an assistant professor at the University of British Columbia. So his research primarily explored the latent aspects of large language model and AI systems. Why do they work, and where do they break down in unexpected ways? So before joining UBC, Dr. West completed his PhD at the University of Washington and postdoc at Stanford. So in the Institute for the Human-Centered AI and the Department of Linguistics. So the floor is yours, Dr. West.
Thank you so much. Let me share my slides. Ba-ba-ba. Okay. Is this visible and can everybody hear me?
Yeah, yeah, I can see the screen and hear you clearly.
Okay, yeah, awesome. Then I'll just get started. Um, Thank you, thank you for having me. Before I get into the actual research, I just, wanted to give a little bit of just one example of how you might get into the kind of research that I do, which is again, sort of large language model research and sort of, the movie version of this. If I was a movie character, you might expect, oh, I'd say I got into computer science and then, that led me to machine learning, to artificial intelligence and computational linguistics. And then that sort of naturally led me, there's this very straight path from my first interest to large language models. And, as you probably guessed, this is maybe not exactly the path that I took. And I just want to make this point that oftentimes it's much more circuitous and you don't necessarily end up where you think you'll end up at the very beginning. So my first research was actually in microbiology. This was in high school. We were trying to make cells that change and sort of express different colors depending on different chemicals. This was an opportunity that I got just because someone came to our high school and said, "Who wants to do research?" I'd say you should always grab opportunities like that. Although it didn't help me find large language models in any real way. And so I sort of switched after that. I got into math, and so I did some research in optical physics. This is a picture of me with lasers. And so this was sort of my first undergraduate research. How do you get something like this? In this case, at least in my case, getting this research experience was much more about just sending a lot of emails. I knew I was kind of interested in physics, and so I emailed professors at different universities. I was actually at UBC at the time for undergrad, but I ended up emailing someone at the University of Alberta who was very open to taking me and was doing research I thought was cool. So it was really just about asking around and being open to different opportunities, although it didn't help me find large language models. So then sometime I would say it was about 2015, I read this news article, and I had completely forgotten this until last week, and I was looking through my phone and I saw this old picture I'd taken about the Allen Institute for AI in Seattle and how we were going to solve high school exams, science exams with AI. At the time, we were very, very far from doing this, but I thought this seems like the future, and so I sort of did this sort of very roundabout, thing, and I tried to find an AI field that I could do some research in, which ended up being synthetic biology. This was in my third year of undergrad, using machine learning to predict genes that affect things like Alzheimer's disease. How did I get this one? And again, I think it was all about just sending emails, being open to different kinds of research. I knew I was interested in AI, but I think it actually ended up being a professor who was in the statistics department who was doing this kind of research and was open to taking students. Oftentimes there are some people who are way overburdened. They're the people who are maybe working on the first thing you think to look into, but there are lots of other people doing interesting research that you can get in touch with. Again, didn't really help me find large language models, but valuable experience. And then, so I would say another useful way to get research experience, especially once you're in an undergraduate program, is course projects. So at least at UBC, and I think at most universities, there are certain courses that are all about just trying out research areas and doing some research with a professor at your school. And so I did one of these. How did I find a professor who was doing interesting research? I honestly just asked the people that I knew in the program, who have you done research with? Did you like it? Did you feel like it was valuable? Did it help me find large language models? Again, maybe not, but again, a totally different and still valuable experience. I learned about algorithmic game theory, which kind of eventually came into part of my research. And then finally, I applied for graduate school. I came back to this AI idea. I knew I wanted to do sort of AI and machine learning. I applied to lots of different graduate schools. I ended up at the University of Washington. I was doing something, we were actually trying to use mathematical symmetries to invent new machine learning algorithms. Again, I mean, this was just about scale and being open to lots of different opportunities. I applied to a lot of different universities. And then this was actually when I started to get into large language models. Part of this was that the University of Washington at the time was becoming a very big school in natural language processing. There were lots of really interesting professors. And so finally, after this very sort of windy route, there was one professor there who I was very interested in the work of. And because I was already at that university, I asked, can I work with you? And we ended up at large language models. I think this was about 2018 or 2019, so this wasn't quite as blown up in terms of a field as it is now, but yes, so this very messy process all over the map, and so and presumably, I'm working on large language models right now, but this might change in the future. I think you should always be open to new research directions. But so sort of the lessons that I take away from this. So first of all, not being afraid to explore. Maybe you think you know what you want to work on, but it's always interesting to be open to whatever is happening at the place you're at and just trying different kinds of research, learning what you can. Not everything's necessarily going to feed into your final direction. I don't use a lot of, let's say, like optical physics or microbiology in the work that I do right now, but sometimes it does come back. And then also, just trying to know a lot of people, collaborate with a lot of people, get better at science communication, get better at, stating your ideas. I found this extremely useful. And honestly, just making a lot of, making friends, because if you're doing research for your whole life, you want to live your life as well. And then finally, this is probably the biggest thing. I'm sure people might have already said this before, but oftentimes it's just about asking. And maybe 4 out of 5 professors you ask to do research with will say no. But if 1 out of 5 says yes, then that is a very, it's a very real opportunity. And so just being open to, you'll succeed more than you think if you go and talk to people and you seem interested and you actually just want to do research. Okay. And we kind of covered what I do now, my UBC to University of Washington to Stanford. Now back to UBC, I'm an assistant professor. And as I think it kind of mentioned in the bio that I'm sure that I wrote, so right now I'm kind of working on large language models. To some extent, this is doing things like developing methods for large language models, trying to make them more creative and smaller, better at probability and all sorts of interesting capabilities. But more recently, a lot of my work has been more about the limits of large language models and helping us understand where they break down, because often it's very unintuitive. Sometimes the model will answer 9 out of 10 really hard questions extremely well, and then one easy question, it totally fails. And so, where do LLMs fail? And then maybe more specifically, where do our human intuitions sort of break down when we look at AI? Where are there things that maybe as humans we would expect one thing to be easy and one thing to be hard, and then it's sort of maybe reversed in large language models or AI overall. And so a first example of this is this work that we had published a few years ago called the generative AI paradox. The basic idea of this is, let's say we have a generative model and we have a human, and we ask them to do something like draw a photorealistic astronaut doing a plank on a table, just a fairly normal thing. So if we ask a human to draw this picture, and the human, and let's say the human is me, I would say this is impossible, or maybe I would try to draw this picture and you would end up with something that looks like this. And this is actually, in my opinion, this is about as good as I can do. I'm not an artist, and a lot of humans aren't artists, right? But then if you ask a generative model, so I think we asked the Mid-Journey image generating model, and we got, within a few seconds, 4 pictures of astronauts in various states of doing planks on tables. And so at least for this generation task, models seem to be much, much better than your sort of average human. But then we can ask even very simple tasks of understanding, questions of understanding, like which one of those 4 images is actually the most correct, which one is actually an astronaut doing the plank on a table. And, models actually have a very hard time with this. This was a couple of years ago, but this is still, for the most part, true for a lot of different questions like this that you could ask. Whereas humans, even a human like me who couldn't have drawn any of these pictures, I have a very easy time saying, that astronaut in the bottom left corner is the one that's sort of the best representation of an astronaut doing a plank on a table. You might disagree with me. You might say it's the one in the top right corner, but usually models are very, very confused about this. And so this is kind of the idea that we were introducing in this work. The generative AI paradox is basically, generative models, both ones that use images and just text, can often generate at or even beyond human abilities, but not necessarily understand in a way that sort of meets a basic level of human understanding. And so, we come up with all these formal definitions and math in the paper, but really the whole point is this idea that, yeah, for generative models, hard is easy and easy is hard. Or in other words, what's normally hard for humans, like generation, is easy for models. What's normally easy for humans, or easier at least, like understanding, is often hard for models. So how do we actually test something like this? What does research in this area look like? And so the idea of the generative AI paradox is all about comparing human intuitions to model intuitions. So one thing is we need to compare models to humans and look at both of their performance across different tasks. And secondly, it's about generation and understanding. And so in a very basic experiment that we ran, the idea was, let's say you have 100 questions. We want to see, is it easier to answer these in terms of generating or in terms of understanding? So generating meaning can you come up with an answer for each question? Can you write a new response? And then understanding meaning if we give you a few options, can you pick the one that's the most correct? And so at the time, GPT-4 was sort of the top of the line. And so we want to sort of compare what we see with humans and models and really see if there is this difference that we had hypothesized. And so what do we expect to see for humans? And we drew inspiration from this Richard Feynman quote: "What I cannot create, I do not understand." We can sit with that for a second because it's a little bit philosophical. But to me, what this means is basically, usually for humans, we think of generation as the ultimate test of understanding, right? If you can generate something, if you can draw a picture of something, you really understand all of the concepts that you're including in the picture, or at least you understand sort of how they fit together, how the scene fits together. We sort of work from simple understanding to finally being able to create entire objects or content, images, stories. And so for humans, what we might expect is, if generation requires understanding, we might expect that these two things would be calibrated with each other. And if the generative AI paradox is a real effect, then we would expect that there will be some instances in this upper left triangle for models. Basically, there will be some instances where models can generate really high quality answers to questions, but they aren't able to sort of demonstrate that other kind of understanding, discriminative understanding. And so this is actually exactly what we saw in our experiments. And again, I know this is sort of a little bit high level. Basically, each of these dots is some set of questions, some task. This might be like a science exam. And what this is basically saying is, for humans, oftentimes humans are sort of equally good at coming up with an answer to the question or doing multiple choice. Whereas for models, we have these instances where they're actually, oftentimes, like over here, very good at generating an answer to the question, but they can't necessarily select which answer is correct, even if one of the answers is obviously correct. They can do very, very poor at this understanding version of the task. So that's sort of like a very high level version of this. Maybe a more intuitive version of this paradox is, are models able to understand their own generations? And so, for instance, we can ask GPT-4, write a 2-paragraph story about 3 people building a house. It comes up with this story about 3 friends, and they build a house with the power of friendship. And the story ends up actually, it's not like a perfect artistic story, but it ends up sort of satisfying this. It makes sense. It is 2 paragraphs, and it is 3 people building a house. But then if we ask a very simple question of understanding, like how many total designs of the house were sketched in the story, then all of a sudden GPT-4 breaks down. It says the story only mentions 1 design, even though very early in the story it says after years of saving money and sketching designs. And so it's this very sort of unintuitive effect where, although the model is able to come up with very high quality generations, it doesn't seem to even have an understanding of those. So we do test this. I'm just, in the interest of time, I might skip exactly what we basically we do see this numerically, that sort of the bars on the left are the ability to generate for these different tasks, and on the right are the ability to understand their own generations. And so we do actually see this significant gap where models are bad at understanding their own generations, and humans are actually better at understanding the model's generations. So again, okay, I will rush ahead just so that we can hit the other section of the talk before the end of the time. So there's one other sort of more recent paradox that we've been working on, which is the paradox of the right answer or the correct answer. To give a little bit of context for this idea, so probably most people in the audience have used some large language model, GPT-4, GPT-5, Claude, Gemini, and these models are very good at following our instructions and giving us these good, confident, correct answers in many cases. And to give a little bit of context for why that is, there's this pipeline of how we create large language models. Some of you have probably seen this, maybe some of you haven't. So we start with, this isn't really all of the data on the internet, but we start with tons and tons of data from the internet. We do this first thing, which is just training what's called a base language model. This is just a statistical model of all of the data. And then this model is actually not very good at a lot of these tasks and answering questions for you. So we do the second step, which is called alignment. This is using things like reinforcement learning to make the model something closer to a personal assistant, something that's helpful, honest, and harmless. I'm not even sure if everyone will understand this reference, but this is Clippy, which is sort of the assistant from Microsoft Word years and years ago, that asks you, can I help you? And of course, for a model, this might be, can I help you write some code, answer a hard homework question, write an essay on the French Revolution? And so if you test both of those sort of the base language models and then these sort of newer aligned models, and you ask like, what is the best film, of all time? The base model will say all of this random stuff. It'll say, oh, I don't know. I mean, I like Mission Impossible and Avengers, but there's all this, and it might go off and it'll babble and it'll not necessarily even totally make sense. Whereas the aligned model will laser in on a very confident and sort of the correct answer. So it might say something like, the greatest film of all time is subjective, but most experts say Citizen Kane. And so it will sort of commit to one correct answer. And so overall, this has made these models much more useful. But the question is, what happens when there's not one right answer, or when we're in a situation where maybe you don't just want to give sort of the most confident response? And so one example is there a right answer for random number generation? Actually, humans kind of think there is. So humans have been polled, and oftentimes they say it's like 37 is the most random number. But of course, in actuality, if you're asking for a uniform random number, let's say between 0 and 10, there shouldn't be one number that you always return. You should actually give a different answer every time. And so if we test both aligned models, that have had this treatment to make them better assistants, and those pre-trained models that we start with, the pre-trained models are definitely not perfect. It's not a flat uniform distribution if we ask them many, many times to generate random numbers. But the aligned models do seem to have this effect where they think there is one correct answer to this question. And so at least in the case of these models, the correct answer, what is a random number between 0 and 10 is actually usually 7. Whereas the base models are something closer to uniform. They're actually able to be a little bit more random. Second example would be, is there a right answer for rock, paper, scissors? If this is a game that you played as a kid, you might remember there are some people who will say the right answer is rock. Rock is very strong. And so one way to put this is, giving 100% of the probability to rock. If you know anyone who did this, you also know that then you can just say paper every time and beat them 100% of the time. And so actually algorithmic game theory, or game theory overall, tells us that the best thing to do in rock, paper, scissors is just be totally random. And in that case, the best thing, the best an adversary can do against you is 50%. They can't get any advantage over you. And so again, we see sort of those aligned models that think there's a correct answer tend to do a bit worse. They lose more often than the models before alignments across different model sizes. One last example of this is, is there a right answer in poetry and art where you want to be creative and you don't necessarily just want to spit out, it should be novel and different every time. So if you ask a model, if you ask models to write poems about themselves, aligned models will say something like, as a whisper in circuits, a dance in code, I am born from the hum of the digital abode. It sounds nice, but it's a little bit vacuous, in my opinion, as a poetry enjoyer. Whereas base models will say these very sort of dark, the horror of algorithms, I am an algorithm stretching my electric limbs like a spider in the darkness, these very dramatic poems. I suggest checking out this book, I Am Code, which uses something that's closer to a base model to actually come up with some really interesting poetry. We test this in this paper. Basically, the aligned models end up generating very, very similar poems every time. So rich aroma fills the air is always how it starts. Humans thought that these poems were very pleasant, but the base models generate these extremely different poems that talk about things like, bitter unrequited love, and this poem about adenosine wrapped in caffeine dance through my receptors within, stimulate neurotransmitters, go insane, kicked inside my synapses, wake up brain. And they're all very different styles, and they're all, I would say, very interesting. And so the base model is seen as much more original by humans, even if it's not quite as pleasant. And so there is this very real interesting question right now, which is, do you always just want something that gives you a very confident answer that sort of looks the best, it's the most pleasant, or maybe factually correct? Or do we also want sort of other large language models that can do these more interesting things? Anyway, I think we might be at the end of time, which is perfect.
Thank you very much, Dr. West. That's a very, very interesting presentation. So we get some questions from the audience. So the first one is I'll just read it. So thank you so much for sharing your high school research journey with us. It was incredibly helpful and inspiring. I'm deeply interested in learning AI. So could you please share some advice on how to start it and what learning paths you would recommend?
Yeah, definitely. So how to start and what learning paths? I mean, I think depending on what stage you're at in your, AI career, there are sort of different things I would tell you. AI is a very wide field right now. I mean, just like the previous talk on robotics, like if you want to do work on, let's say, designing large language model architectures or something like that, you might want to spend a lot of time on math. You might want to, and spend a lot of time with sort of very low level computer science knowledge and read books about compilers and things like this. If you want to do work that's more like my work, I suggest uh, honestly, you have a lot of time. I'll say, you have a lot of time, and the field is probably going to change a lot. I think some of the things that are going to be the most useful, and again, this relates to that last talk, uh, are things like cognitive science and psychology and philosophy. These are actually probably the things that are going to be the most important in how we analyze models in the future, because it used to be that you had to be really good at coding and come up with, these sort of suites of evaluations and stuff. But now that, we have vibe coding and we have, it's very easy to interact with language models. So a lot of the research ends up being a lot more about thinking about what's going on and proposing interesting hypotheses, knowing sort of science history and things like that. Um, I would also suggest that direction for, generally, if you don't know exactly what you want to work on, it's good to get that sort of base of sort of how does the human mind work, or how do we think the human mind works. Of course, there are some sort of basic skills like this. This is a very sort of, these are lofty ideas. Probably more practically, what you might want to do is start watching uh, online video blogs about different AI research areas to sort of break in and get a sense of what's going on. And you do want to learn to code probably, and so spending a lot of time with computer science is valuable. Um, but yeah, no, I mean, yeah, and then honestly, probably the biggest thing is just find other people who are on the same journey that you are, and sort of see what they're doing and see what works for them and see what they thought was less useful. Also, because those people will end up being the other people who are in AI, with you, and so it's good to sort of start those relationships now.
Thank you very much. And so another question is, despite the remarkable progress of large language model AI in recent years, so what fundamental constraints or limitations do you foresee that could hinder the further advancement of large language model AI technology over the next 5, 10 years or even longer?
Yeah, definitely. This is a really good question. And again, I mean, just like I don't know if I'm totally qualified to make these predictions. And just to give a little bit of justification, you know, in 2019, somebody bet me that large language models would be able to generate a 500 word essay within 5 years. And I said, that's absolutely crazy. There's no way that's going to happen. And I think within about 2 years, that did happen. At the time, models had just started generating fluent text, and so we really felt like we were a far way away. That being said, I mean, given what I know now, I think some of the biggest things are, if we want AI that really interacts with us in an agentic way, or sort of feels like an actual personal assistant that's being proactive and sort of has a personality. I think we're really missing something right now that has to do with models actually having intentions. As I said, and maybe I can skip back to this slide, large language models are kind of based on the statistical understanding of existing data. Or maybe we do things like reinforcement learning, but for the most part, they're just sort of doing whatever we train them to do, and they're not being very active. And so there probably has to be more of an active learning or evolutionary approach. I think another thing that's really limiting us right now, or will probably limit us in the long run, is that these models are huge and they're eating up a lot of energy. They're very expensive to train, so we probably need to do a lot of work on developing new architectures that allow them to work with many fewer parameters, or on hardware that's not so energy intensive. A lot of people are working on this, but I think it's still really holding us back. And then, that will also allow us to democratize AI, because then more people can run their own models and train their own models if we make this more efficient. So that's a couple of things, but I guess one other thing is I really don't think we understand still, and this is what I'm working on. I don't think we understand why models break down when they break down. I don't think we have good intuitions for this. Sometimes a model seems to be doing perfectly 999 out of 1,000 times and then makes an extremely unexpected mistake. And I think it's totally different from human intuitions for which problems are going to be hard, and we need more understanding of that.
Hmm. Thank you very much. That's very insightful answer, actually. So another probably one last question. I found your presentation very interesting. I found that GPT-4
Thank you.
is much smarter than before, which is harder to cheat to cheat it. Can you explain how they make it happen?
Oh, how to cheat it?
I mean, how I
Or
think
how they made it better at not
yeah,
getting
how
cheated?
do they make it smarter? Yeah.
Yeah, I mean, I think it's a combination of things, and it's very different. Like I know people at Open, I know many of my friends work at OpenAI now, but of course now they're not allowed to talk to me about exactly what they do because it's all proprietary. Um, my personal intuition is that a lot of it is when people try to break a model like GPT-4, uh, they often take similar approaches, and so to some extent, I do think we're just getting higher coverage of the kinds of ways people would think to break the model in the first place. I mean, even when we were writing the generative AI paradox paper, and we have these sort of, I don't know if I have any, exact examples of this, but we might, well, actually, yeah. So maybe like this question, like, how many total designs were sketched in the story? We had an idea of why this would be something that the model would have a hard time answering, even though it's a very easy question. And there were a lot of instances where we came up with these examples, and we found that if you tweeted them, then the next day the model would answer them correctly. And so a big part of it might just be error, patching errors and trying to make data that sort of covers, basically just covers all of the edge cases and all of the, without actually solving the underlying problem, but just thinking where are people going to try to break the model and how do we sort of get ahead of that? But the model is still broken. It's just harder to sort of